It sits on the ramp, black, massive, leaking fuel, not from a cracked line, not from a failed seal, from every panel joint on the entire aircraft, fuel dripping steadily onto the concrete below. The ground crew doesn't panic. The pilot doesn't abort. This is normal. This is how the SR-71 Blackbird sits on every ramp before every mission, leaking. Because it was built that way, not because someone fixed them on purpose. And in 3 hours, that same aircraft will be traveling at Mach 3.2, faster than a rifle bullet, at 85,000 feet above the Earth. The fuel leaks will stop because at that speed, at that temperature, the metal will have expanded enough to seal every gap on its own. The aircraft that leaks on the ground becomes watertight at Mach 3, and that is only the beginning of what makes this machine unlike anything else ever built. Here is the question nobody asks about the SR-71. Most people know it was fast. Mach 3.2, 3,440 kilometers per hour, New York to London in under 2 hours. Most people know it was high. 85,000 feet. You can see the curvature of the Earth from the cockpit. The sky above is not blue. It is dark indigo, transitioning to black. But nobody asks what it actually feels like to build a machine that moves that fast. What problems appear at Mach 3 that simply do not exist at Mach 0.9? What materials you need? What engineering solutions you have to invent because nothing that existed before was adequate? The SR-71 was not a faster version of existing aircraft. It was a machine that required entirely new answers to entirely new problems that had never been encountered before. And the fuel leak on the ramp is where those answers begin. At Mach 3.2, aerodynamic friction heats the aircraft's skin to temperatures that vary by location. The leading edges of the wings reach approximately 290 degrees Celsius. The fuselage skin reaches 230 to 260 degrees Celsius. The engine inlets, the most thermally stressed external components, reach over 400 degrees Celsius. These are not temperatures that aluminium can withstand. At 175 degrees Celsius, aluminium alloy begins to lose structural integrity. At 230 degrees, it is unusable as a primary structural material. The SR-71 cruises at temperatures that would destroy the material used to build every other aircraft of its era. Lockheed's Skunk Works team, led by Kelly Johnson, had one option: titanium. Titanium maintains its structural properties up to approximately 550 degrees Celsius. It is approximately 60% heavier than aluminium, but vastly more heat-resistant. Its strength-to-weight ratio at elevated temperature is unmatched by any material that was accessible in the early 1960s. The SR-71 is approximately 85% titanium by weight. Building it required solving problems that the titanium industry had never encountered. Titanium is extraordinarily difficult to machine. Standard cutting tools wear out almost immediately. Coolants used in conventional machining react with titanium and cause hydrogen embrittlement, weakening the metal at a microscopic level. Lockheed had to develop entirely new machining techniques, new cutting tool geometries, new coolant formulations, and then train an entirely new workforce to use them. The fasteners holding the aircraft together also had to be titanium, because steel fasteners expand and contract at a different rate than titanium panels, and at Mach 3 thermal cycling, the differential expansion would eventually work the fasteners loose. Even the paint had to be reconsidered. The black color of the SR-71 is not camouflage. At 85,000 feet, visual detection is irrelevant. No aircraft can intercept it. No missile of the era could reliably catch it. The black is a thermal management decision. Black surfaces radiate heat more efficiently than any other color. At Mach 3, The aircraft must shed heat continuously, or the internal temperature of the fuselage, where the fuel tanks, avionics, and crew are located, will climb beyond survivable limits. The black paint radiates approximately 30% of the aerodynamically generated heat directly back into the atmosphere. Without it, the aircraft would cook itself. Now, back to the fuel. The SR-71 burns a specially formulated fuel called JP-7. JP-7 was developed specifically for this aircraft. Its flash point, the temperature at which it ignites spontaneously, is exceptionally high, approximately 60 degrees Celsius. For comparison, standard Jet A fuel ignites at approximately minus 40 degrees Celsius. JP-7 is so stable that you can extinguish a lit match in it. It will not ignite from a spark. It requires a specialized chemical ignition system, triethylborane, or TEB, injected directly into the combustion chamber to initiate and sustain combustion. The reason for this extreme stability is the heat environment. At Mach 3, the fuel in the SR-71's tanks is not merely a propellant, it is the primary heat sink for the aircraft's systems. Avionics, hydraulic fluid, and other heat-generating systems route their thermal load into the fuel, which absorbs it and carries it to the engines where it is burned. By the time the fuel reaches the combustion chamber, it has already absorbed significant thermal energy from the aircraft's own systems. If the fuel were less stable, if it had a lower flash point, it would ignite prematurely in the tanks, in the lines, or in the heat exchangers before it ever reached the engines. JP-7's extreme thermal stability is not a fuel property chosen for convenience. It is a survival requirement for the aircraft. And this fuel, this extraordinarily stable, high flashpoint kerosene, leaks out of the aircraft on the ramp through the panel joints because the titanium structure contracts at ambient temperature, opening gaps too small to see but large enough to drip. The engineers at Skunk Works faced a choice. They could design the tanks and panels with seals that closed the gaps at ambient temperature. But those seals would fail at Mach 3 temperatures as the metal expanded by several centimeters. Or they could design the structure to seal itself at operating temperature, accepting the fuel leak on the ground as a permanent feature of the design. They chose the second option because the aircraft was never designed to operate on the ground. It was designed to operate at Mach 3 and 85,000 feet. Everything else, the ramp, the taxi, the takeoff, was the unavoidable transition. After takeoff, the SR-71 immediately proceeded to an aerial refueling from a specially modified KC-135Q tanker. This refueling served two purposes. First, it topped off the fuel tanks, which had drained on the ramp. Second, it gave the aircraft the full fuel load required for its mission without carrying it on the ground, where the heavy fuel load would stress the contracted, leaking structure. After refueling, the SR-71 accelerated. The acceleration itself was a managed process. At subsonic speeds, the J-58 engines operated in conventional turbojet mode. As the aircraft approached Mach 2.2, the engine inlet geometry changed automatically as movable spikes in the center of each inlet translated rearward. At Mach 3, the engine transitioned to a mode closer to a ramjet than a turbojet, with the majority of thrust coming from the inlet compression and the turbojet core functioning primarily as a fuel pump. The inlet spike position was managed by an analog computer that calculated the precise geometry required to position the shockwave at the inlet lip. A shockwave positioned 1 inch too far forward or too far rearward could cause an inlet unstart, a violent pressure disruption that asymmetrically unloaded one engine and produced a yaw moment violent enough to throw the crew against their harnesses. Inlet unstarts were common during the early SR-71 program. They felt, to the crew, like being hit by a truck from the side. The final solution, an improved inlet control computer and more refined spike scheduling, reduced unstarts to rare events. But they never disappeared entirely. At Mach 3.2 and 85,000 feet, the SR-71's only defense was its speed. No jamming system could reliably protect it. No evasive maneuver was possible at those speeds. Turning radius was hundreds of kilometers. If a surface-to-air missile was launched at the SR-71, the standard procedure was to accelerate. Not evade, accelerate. The missile, designed to intercept a target at a specific predicted position, would arrive at that position to find the SR-71 had already moved beyond it. No aircraft or missile system ever successfully intercepted an SR-71 during its operational service. Over 4,000 missiles were fired at SR-71s during reconnaissance missions. 0 hits. The aircraft that leaked fuel on every ramp in every country it visited that required a unique fuel, a unique ignition system, a unique titanium supply chain, and a unique ground crew, was simultaneously the most vulnerable-looking and most survivable aircraft ever built. Its vulnerability was on the ground, its invulnerability was at speed, and everything that made it leak when it was cold was the same engineering that made it untouchable when it was fast. If you want to understand the aircraft that the Soviet Union built to try to intercept the SR-71, the MiG-25 Foxbat, its design compromises, and why it ultimately failed at the mission it was created for, I've covered that in full detail in another video,